Welcome to today's lesson on limits and discontinuities. We will explore the different types of discontinuities. First, let's define discontinuity. A function is discontinuous at a point when certain conditions fail. These conditions include if the function is not defined, or if the limit does not exist at that point. Another condition is when the limit does not equal the function's value. Discontinuities can be classified into several types. Now, let's move to our first problem. We have the function f of x equals x squared if x is less than 2, 4 if x equals 2, and x plus 1 if x is greater than 2. Is f of x continuous at x equals 2? To determine this, we check three criteria. First, f of 2 equals 4. Second, the limit as x approaches 2 from the left is 4. Finally, the limit as x approaches 2 from the right is 3. Since these limits do not match, f of x is discontinuous at x equals 2. Next, let's discuss removable discontinuity. A removable discontinuity occurs when the limit exists, but it does not equal the function's value. This can usually be fixed by redefining the function. Consider the function g of x equals x squared minus 4 over x minus 2. Does g of x have a removable discontinuity at x equals 2? First, simplify g of x. It simplifies to x plus 2 for x not equal to 2. The limit as x approaches 2 is 4. To remove this discontinuity, redefine g of 2 equals 4. Now, g of x is continuous everywhere. Now let's discuss jump discontinuity. A jump discontinuity occurs when the left limit and right limit exist, but they are not equal, creating a jump in the graph. Consider the function h of x equals 3 if x is less than 1. 5 if x equals 1, and 7 if x is greater than 1. Is there a jump discontinuity at x equals 1? The left limit is 3. The right limit is 7. Since they do not match, there is a jump discontinuity at x equals 1. Now we will talk about infinite discontinuity. This occurs when the limit approaches infinity at a point. Often this happens with vertical asymptotes. Analyze the function k of x equals 1 over x minus 3. Does this function show an infinite discontinuity at x equals 3? The limit as x approaches 3 from the left is negative infinity. The limit as x approaches 3 from the right is positive infinity. Since the limits diverge, k of x has an infinite discontinuity at x equals 3. Next, let's discuss oscillating discontinuity. This occurs when a function does not settle at a value. The limit does not exist due to oscillations. Consider the function m of x equals sine of 1 over x. Does m of x have a discontinuity at x equals 0? As x approaches 0, sine of 1 over x oscillates. It oscillates between negative 1 and 1. The limit does not exist, confirming an oscillating discontinuity at x equals 0. Now let's move to identifying discontinuities graphically. Look for breaks, jumps, or asymptotic behavior in the graph. Assess the value at the point compared to nearby points. Consider the piecewise function n of x equals negative 1 if x is less than 0, 1 if x equals 0, and 2 if x is greater than 0. Sketch the graph and identify the discontinuities. The sketch shows a jump from negative 1 to 1. Thus, we confirm a jump discontinuity at x equals 0. Now, let's identify discontinuities algebraically. Find discontinuities by simplifying functions. Check the limits piecewise. Look for terms that cause division by 0. Consider the function p of x equals x squared minus 1 over x minus 1. Does it have a discontinuity at x equals 1? Factoring gives us p of x equals x minus 1 times x plus 1 over x minus 1. For x not equal to 1, this simplifies to x plus 1. The limit as x approaches 1 is 2. But p of 1 is undefined, making it a removable discontinuity. Now, let's conduct a comprehensive case study. Consider the function q of x equals x squared if x is less than 0, 3 if x equals 0, and sine of 1 over x if x is greater than 0. Let's identify the types of discontinuities in q of x. For x less than 0, the function behaves regularly. At x equals 0, q of 0 equals 3. But the limit as x approaches 0 from the left is 0. The limit as x approaches 0 from the right oscillates. Thus, we confirm a removable discontinuity at x equals 0. There's also an oscillating discontinuity at x equals 0. Thank you for joining today's lesson on discontinuities.